Heavenly Father, thank you for this day, for what you're doing in my life. You're working in my life. And I thank you for that. Thank you for the amazing grace that is real. It's not yesterday's, it's not some old stuff in the past that we gotta kind of blow the dust off. It's so alive and so real, and I thank you for making life like that. Not easy all the time, but blessed and enriching and dynamic. So hallelujah. Father, I pray your blessing on this class. I can ask that. I mean, I pray before we have class. That's just what you do, I reckon. And so asking you to bless each one. I did that this morning. And I don't know how to do it. I don't even know how to tell you to do it, which is probably a good thing. But you know each one in this class, and you know where they have struggles, where they're concerned, where they may even be worried or anxious about things, or facing things that nobody but them would know. And you're able to address those things so your handwriting would be honest, and it wouldn't be just something that they'd have to try to manipulate in their brains that you did something, but something that you would just manifest, your presence, your care and love for them, the reality of who you are that you just manifested. These in this class, Father, this is the one I'm teaching, so you can do that. And even to the ASIC students that I've never met, some of them, but you can work those things out as well. And I pray you would in Jesus' name. Amen. Okay. So, changes of state, I passed out that was in the front of where you are.
So the printer evidently did not print my second page. Would it be okay if I got this to you after class?
Got what to me?
It's the observation. I had 2 pages and the printer just didn't print it. I just print it.
Okay. Okay, yeah, so, but I was reviewing this lesson. This seems to plug in here. So, one of my favorite places, I mean, there's not a wide variety here in Jackson, Kentucky, of places you can eat, but one of my favorite places to eat, they have these things. They have tanning beds. So I'm gonna digress and talk for a minute on these things. Because it's just like people get married here, and you just assume that they'd have devotions together. I just think, well, that'd be common denominator. I mean, they've been by the Bible school, they've heard from probably most every professor, and they've heard from people all over the place that, you know, it's important to have devotion together. I mean, you don't have to do a Bible study together. My wife and I could never, we prayed together every morning. And that helped to deal with things, because if we're carrying something, you know, to bow and pray effectively and not just say words, you know, you had to deal with it. But we prayed together every morning. Once we read it up a devotional. But as far as having a Bible study together, some couples have had Bible studies together and done great. We just never could. It just never fit. I think I proceed through something different than she does, and so it's better for us to do our Bible study different. We can talk about something, our devotional may say. So anyway, what does that do to tanning? Well, I don't know. But that's what you get. So, and there's stuff, I went online to look at, I mean, I've done this before, but I went online to look. There's a lot of old stuff. And so I just tried to find some more recent stuff. And there's one that was put up about 13 days ago and one put up a year ago that are good. And the one I have, when I put this up in your lessons, it'll be there. It's a link to a BBC Good Morning BBC or Good Morning Britain or something, one of those Good Morning America stuff. So they're talking about, and they're interviewing 2 people, and it's a nice interview. It's not just, oh yeah, it's the worst thing in the world. same as cigarettes. You know, it's not like you just get one side, you get two sides. You get somebody that's not for it, but can see that there are a lot of things. So this tanning stuff. So, yeah, number 5, it's boring. Yeah, okay. Well, anyway, they have music there, so you can listen to some music. If you were to lay in the coffin bed, the wrinkled raisin look, yeah, somebody on this program said, you know, if when you're 50, you don't want to look like a purse. I thought that was pretty funny. But anyway, this wrinkle thing, I mean, it'll happen. I have a cousin that looks like she's probably 20 years younger than me, but she looks like she's probably 15 older. She worked in New Mexico or Arizona for years as a teacher, but she spent a lot of time in the sun. So I don't know, but that's just one. Can't build a case on one, but anyway, you increase your risk of getting skin cancer. So that's this deal. Brown now, blue later. That's skin cancer is not a nice thing to have. And it's not that every tanning bed does the same kind of thing. If they did it like they probably should, and communicate the dangers of it, and evaluate how many times you've been, and what, you know, how long you sat under or laid under it. If they did those things, so there'd be somebody to give you a quick check saying, well, you know, you should probably back off a little bit for a couple days or whatever. But that, some of them write it up and say that they do, but experience has shown that people just don't. People that are working there get busy and don't say that, or don't go through all that. Okay. So most people think tanning beds can tan their skin safely without the hazardous side effects. That is not true. There's no such thing as a healthy tan. Tanning beds give off at least twice as much ultraviolet UV radiation as sun does. The rays from tanning beds are long-wave UVA rays instead of short-wave UVB rays that you get from the sun. Now this is interesting because gamma rays, which are high-frequency rays, as you remember, penetrate, I mean, they go deep into your body. I mean, because they're high frequency. This is a little bit different. The UVA, which are longer, penetrate deeper into the skin. They get down to the epidermis, I believe. So UVA rays don't burn your skin like UVB rays do, but they do bore deeper into your skin and cause more permanent damage. So the sun's ultraviolet A, which is long wave, relatively speaking, in terms of ultraviolet rays. So you've got visible, you've got ultraviolet, and you've got infrared. Infrared are the longer, ultraviolet are the shorter, but then within that branch, you've got these three categories, A, B, and C. Ultraviolet A, B, and C. A are the longer waves, B are shorter than longer, and then C are even shorter. So that's what you've got. They're all ultraviolet, but they're at different wavelengths, you know, nanometer thing kind of stuff. So it was once thought that only UVB, the shorter of the two, was of concern. We keep learning more and more about the damage caused by UVA. The new improved forms of protection against UVA keep emerging. Keeping up with these new developments is a worthwhile challenge that can help all of us prevent sun damage. Okay, UV radiation, as you remember, part of the electromagnetic spectrum that reaches the Earth from the sun. It has wavelengths shorter than visible light, making it invisible to the naked eye. UV are classified in three ways, A, B, and C. The longest of three, and that's in nanometers, so it is divided into two ranges, UVA1, UVA2, and then you've got UVAB and UVAC. And UVAC are usually absorbed in the ozone layer. That's why it gets heated up faster, because it's absorbing, and when it absorbs, it collects heat. So they absorb stuff, heat happens, so the temperature in the ozone layer is higher than it would be down below, but not because, you wouldn't feel it. You'd probably stick your hand out there and not feel any heat because there's so few molecules, but the ones that are there are moving fast because they're taking in this. So this is what we got. This is A, B, and C. So A's cut through, B's get terminated, C's get intercepted by the ozone. Now it does intercept some of the B range, and so that's what smoke there and climate change all over the place. That's facetiously said, I don't believe it. But I lost my place here. I guess that shows me now. Okay. Here we are. So visible light, UVA A and B. And A is broken in a couple places, but right now it's not that important. So, what does it do? Both UVA and UVB rays, however, penetrate the atmosphere and play an important role in conditions such as premature skin aging, eye damage, including cataracts, skin cancers. They also suppress the immune system, reducing your ability to fight off these and other maladies. So, in the beginning, when God created this thing, this was probably not an issue. Things were designed before the flood to accommodate this stuff. So you didn't have, it wasn't designed for aging like we know it now. And part of the aging process, especially after the flood, where you've got a complete different climate going on, then we're more susceptible to this stuff. So damaging the skin cellular DNA, excessive UV radiation produces genetic mutations that can lead to skin cancer. I go to the VA and they look at my skin, and I've spent 15 months in Hawaii working on the beach, knocking down green coconuts and eating the spoon meat out of those things at lunch. I mean, it was 90 degrees all the time, at least down in the, because it was sweet. Diving, learned to scuba dive. I mean, it was just great. Except you're out in the sun all the time with as little clothing as possible. At least that's where most of anybody I knew and myself were, so it wasn't the best. So I never used block. I've never used block ever. That stuff. I thought it's not manly. That was probably stupid. But anyway, back in that day, I majored in stupid, so that would naturally be something I would have done. So anyway, most of us are exposed to a large amount of UVA rays, as it said. That isn't blocked by the ozone layer. They're longer wavelength, they come right on in. Through our lifetime, but UVA rays accounted for 95% of the UV radiation reaching the Earth's surface. They are less intense than higher frequency waves, but they're 30 to 50 times more prevalent. They present with relatively equal intensity during all the daylight hours throughout the year. Okay, they penetrate the skin more deeply. That was the deal. I had to go over that a couple of times because it just seems inconsistent with X-rays and gamma rays being really dangerous because they go down and mess up internally. But the longer wavelengths, here's a picture of them. So UVA ray, UVA A, go down here to the subcutaneous layer, and UVB don't go down so far. So anything that's digging into your body that deep is questionable. A tan results from injury to the skin's DNA. The skin is reacting to these rays and trying to build some kind of protective measure to stop them from penetrating. So it's an imperfect attempt to prevent further DNA damage. These imperfections or mutations can lead to skin cancer. It's not that everybody's going to get skin cancer, but it's just this whole everything I'm saying right now, because we just finished talking about UV rays and that. I would have missed it had I not been thinking about it this morning, thought, wait a minute, I had something on tanning somewhere, and I actually located it. So, not surprisingly, people who use tanning salons are 2.5 times more likely to develop squamous cell carcinoma and 1.5 times more likely to develop basal cell carcinoma. According to recent research, first exposure to tanning beds in the youth, particularly youth under 30, in youth increases melanoma risk by 75%. So you don't get that if you just eat at showtime. Eating at showtime is a pleasurable experience. The only thing you might do, if you did it a lot, would be to gain weight. And I guess that can have its downside too, but otherwise, so there's Sleeping Beauty. So at the end of this,
That's Snow White.
Snow White, yeah, that's right. Well, she's sleeping and she's a beauty, so I guess it's kind of, you're right at both, well, we're both right. So this thing right at the end of this deal, this website, is a thoughtful conversation about sunbeds by the UK. So it was, I enjoyed it, it was reasonable presentation, I thought. So that's what you get. Probably won't question you too heavily on that. Okay, changes of state. Now we're getting into some stuff that's all around us, but this part of this class has, as I said before, has been I guess out of the parts we've gone through, probably the more difficult. And I don't stress memorizing long names for things because personally, I don't do well with that. I mean, I just want to kind of have an idea about what it does. Well, knowing what it does is important in this part. To understand our weather, we need to understand what's going on with changes of state, and I'm not going to get into formulas. There may be a couple, but I usually avoid them because I'm not expecting you to come out of this class knowing formulas. But if you understand the process, it's, so here we go. Water is the only substance that exists in the atmosphere as a solid, liquid, and a gas. It's just amazing. God is big. And is made of hydrogen and oxygen atoms bonded together to form water molecules. So water molecules are H2O. 2 hydrogen, 1 oxygen. That's the typical water. You can get super water, just like you can superheat and super cool things, but that's a departure that I'm not gonna make right now. So these molecules are bonded together. Here we go. In all 3 states, the ice, liquid, and gas, the water molecules are in constant motion. The more vigorous the movement, the higher the temperature. So all these molecules are moving. And that's where we have Fahrenheit, we have Celsius. Kelvin is a measure of how fast these things are moving. So temperature also is related to these things moving, but there's more to heat than just temperature. And that's why we're gonna do it. But all these are moving. These in ice are still moving. These are moving faster, and these are moving still faster. So they're all solid, liquid, and gas. Now you need to know, you are gonna get this, the next couple things. Water vapor is the most important gas in the atmosphere. It's a little part of it. Like, it's maxed out at 1%. So, because we've got, 78, 79% nitrogen, 21% oxygen, 1% argon, and then there's a 1% left, but the part of that is water vapor. But that little water vapor is the most important gas in the atmosphere. It's an important heat absorbing gas, and it's the source of all, like every bit of condensation and precipitation. It's the source of all of that. The process of water changing state between solid, liquid, and gas requires that heat be either absorbed or released. If it's absorbed, it raises the temperature. If it releases, it lowers it. So, and we'll get to that. In fact, we'll get to that. Then I'm not gonna, I didn't know this. Well, I did before I didn't before I studied it out and wrote this out, and that's been a while. But 1 calorie is the amount of heat equal to heat 1 gram, and a gram is less than 4 100ths of an ounce of water, 1 degree centigrade, like from 14.5 degrees centigrade to 15.5. That's what 1 calorie is. A calorie is extremely small unit of energy. The average person requires about 2 million calories per day. Now, we don't think about that. I look at these little crackers I like to eat, a little pack of crackers, snack crackers. They've got more calories than a can of Mountain Dew. So I combine them. So it averages out. But they usually designate it, as this says, it's usually designated as 2,000. But what it really means is 2 million. So they put this 2,000 calories, but that's kilocalories, so really it's 2 million as far as calories. I mean, you talk about like a Mountain Dew is 170 calories, that's what it says. So it's 170 kilocalories. There are a lot of them, but it takes a lot. It takes common designations makes us think, well, it's just this many, and that's not too many, but anyways, it's more than that. So latent heat. And this is the other stuff is pretty self-explanatory. I mean, it makes sense. This you might have to think about. I would assume, I didn't pay attention in science, so I can't tell you what I didn't learn in high school. But you probably have had this. Some of you have had all this stuff before. You can go online and find stuff that's talking to high school students on this stuff. So, example is melting ice. So here you have, and this is what this says. So you've got ice here. And you start putting energy. This is energy added. You're adding heat to this thing. And this is the temperature of this, ice, water and steam. So this is the temperature in degrees centigrade. So right here is 0, so that's freezing. So you have this ice, and you begin to add energy to it. Begin to heat it up. And so it heats this ice up until you've got ice and water. And when you have ice and water, the temperature doesn't increase. You add heat, but the temperature doesn't increase. What happens is all the heat goes in to break the bonds, because the ice is held together with hydrogen bonds. The little hydrogen atoms in there are bonded together. So what has to happen, and those bonds have to break. And when those bonds are broken, then the little molecules start to move faster. But as far as heat, you have this level. This stays the same temperature until all the ice is melted. This is going to stay at the same. There's heat added to this that is melting the ice, but it's gonna keep melting, it's gonna keep breaking the bonds until there are more and more bonds to break, and then you've got water. And then if you start continue to add heat to this water, you begin to heat the water. So the water gets hotter and hotter and hotter. This is what this is. This ice began to melt. You add heat to it, you keep adding heat to it. Well, the temperature of this doesn't change. It's 0 degrees or 30 degrees Fahrenheit. It stays the same. It doesn't increase because you're just breaking bonds. And then when you come to the completion of all the ice that's there, the bonds being broken, you've got water. And then temperature-wise, you add heat to it, and temperature increases until you get up to 100 degrees, which is 212 Fahrenheit, which is boiling. The water is at the level of boiling point. You get the same thing. You keep adding heat to this because it takes more heat to separate the water and steam. You keep adding, and so this is level at 100 degrees. And you keep adding in more and more energy, and pretty soon you get to a place where you get steam taking off here. So the leveling places are where bonds are being broken. And here the water bonds are being broken. And you're going to be get water and steam. Like here, you got more ice and less ice and less ice as you get to here, and pretty soon you've got only water. Well, here you've got water and steam, and you could continue until you've got all steam. But here you've got a mix of water and steam, and it's until all the water molecules, that the bonds are broken, you're still going to have a constant temperature. So the temperature is constant here at 32 degrees or 0 degrees Celsius, and here at 100 degrees Celsius. They're constant until all the bonds are broken. And when all the bonds are broken, you got steam here. When all the bonds in ice are broken, you got water here. But you keep adding heat to this, and the bonds keep breaking. Okay, when a substance like water is in the process of melting, all the added thermal energy goes to overcome the forces holding the particles together, the crystalline bonds in the solid state. So it holds them, and you keep adding thermal energy, and it breaks bonds. None of the added thermal energy increases the kinetic energy. In other words, you're not increasing the movement of the particles here until all the bonds have been broken. That's why this stays at a constant temperature. The molecules aren't moving any faster all through this part where the bonds are being broken. When all the bonds are broken, then you start increasing the movement. The movement of the molecules start going faster and faster and faster until they get to this point. And then they level off again, and they're getting faster, they're going faster and faster and faster as you get to here, or they're breaking bonds, but they're not moving faster until all the bonds are broken, and then they can go up. So, none of the added thermal energy increases the kinetic energy of the particles. It doesn't make the molecules move faster, it just goes into the breaking bonds. So breaking bonds here, and then when the temperature rises, you're causing an increase in molecular activity. And then it comes to a place where it can't increase anymore until bonds are broken. And so you got to have that whole section that's at the same temperature where bonds are being broken, and then you get finally to a place where they're not. So, because heat energy invested to break bonds is not associated with temperature, so it's not associated with temperature to break the bonds. That's why it's called latent heat. Latent heat. It doesn't change the temperature. If you put a thermometer here, it would say the same thing. While the bonds are being broken, they're being broken, but they're not moving any faster. You're just breaking bonds. Finally, all the bonds are broken, then you'd see molecular action, an increase in temperature up to here, and then you'd start to be breaking bonds again, molecular bonding. That would be being broken, but this would all be the same temperature. Same temperature. This would all be the same temperature until you reach this point. And then you got steam and you got, again, an increase in temperature. And it's working the same way back. As you cool this, if you cool steam down to this level, then you've got water and steam. Well, as things are bonding, as things are bonding along here, the molecules are bonding, the temperature doesn't change, and then once they've all bonded, then it'll decline until you get to this place. It'll go both directions. Okay. Once the solid is completely all melted, all the crystalline bonds are broken, then any added thermal energy begins to increase the motion of the particles and the temperature of the water rise. Now, I'm going to show this in 6 minutes. I've watched so many of these things, trying to get one that is what I want. That's not too technical. I don't need a graduate level physics class describing these things. I want something simple, so people without a scientific background, maybe some of you don't have one, in past classes they don't necessarily, and so this is simple. Unfortunately, I don't know if you've dealt with a lot of international students. I have, so listening to somebody talk, obviously that their English isn't their main language, don't get distracted. Don't, what he says is simple and clear. It's the simplest and clearest I've seen in, I don't know how many I've watched. I've watched a couple handfuls of them. So this was the best. Although if I was choosing, I wish it was done by somebody that had mastery in English. I mean, they know English and you're not gonna struggle with what they're saying, but some people can get sidetracked. Like there was a professor here once that had some idiosyncrasies, and he was a good teacher. He said really good things. But most of the class, at least my wife and I were in of his, we loved it. He said some really profound things, but most of the students were so distracted by his idiosyncrasies that they didn't get anything. All they could see was his idiosyncrasies. They didn't hear what he said at all. So I hope that's not the case in this class, because I've got my share. But, so we're gonna watch this for 6 minutes. Well, I won't watch it all. I think I'll close it at 6. But
this video will provide a detailed explanation of latent heat and sensible heat. These are two types of heat. Let's look at an example to understand this topic easily. We can take water in a completely closed container. Now, we can heat this container. The heat will be transferred to the water little by little. The transferred heat will cause the water temperature to increase. We can measure this with a thermometer. This measurable heat is called sensible heat. If we continuously heat the water, its temperature will increase and reach 100 degrees Celsius. However, after reaching 100 degrees Celsius, the water temperature will not increase further. Even after reaching 100 degrees Celsius, the heat we apply will be used to convert the water from a liquid state to a vapor state. This heat required for evaporation is called latent heat. The water's temperature will not increase until all of the water has evaporated into vapor. Once all the water has evaporated into vapor, the temperature of the vapor will start to increase. Let's heat this vapor up to 120 degrees Celsius. At this point, the vapor contains both 120 degrees Celsius sensible heat and latent heat, the heat used to evaporate all of the water. Unlike sensible heat, we cannot directly measure latent heat. Let's understand what happens here in a more technical way. water molecules are all joined together. When we give heat to water, these molecules vibrate a little. When we give heat continuously, the vibrations of these molecules will increase. The molecules will vibrate until they reach 100 degrees Celsius. When we give heat above 100 degrees Celsius, the joints between the molecules break and each molecule escapes from the water surface and converts into vapor. Here, latent heat is not a special type of heat. It is the same heat that we give to the water. The heat we give makes the molecules vibrate is the sensible heat. We measure the temperature based on these vibrations. When we give less heat, the molecules vibrate less, so the temperature is lower. When we give more heat, the molecules vibrate more, so the temperature is higher. If the heat we give is used to break the joints of the molecules and make them escape from the water surface as vapor, is called latent heat. Now, the temperature of the vapor is 120 degrees Celsius. After reaching 120 degrees Celsius, we can now cool this vapor. When we cool the vapor, its temperature will decrease and reach 100 degrees Celsius. After reaching 100 degrees Celsius, this vapor will release the latent heat it has absorbed and condense back into a liquid. The vapor's temperature will not decrease below 100 degrees Celsius until it has completely condensed into a liquid. Once it has completely condensed into a liquid, the temperature of the liquid will start to decrease. Water doesn't evaporate only when it reaches 100 degrees Celsius. Water can evaporate at any temperature. For example, we can take water in a bowl at 30 degrees Celsius. Now, the molecules on the top surface of this water will use the surrounding heat as latent heat and evaporate. But this process is a very slow process. So, what we learn from this explanation is, latent heat is added to a liquid to make it evaporate into vapor. When latent heat is removed from a vapor, it condenses back into a liquid. When latent heat is released from a vapor, it becomes sensible heat. Let's see what effect this has on HVAC. So I believe that you have a good understanding of latent heat and sensible heat from the explanation above. Now, let's consider a house. It is summertime, so the outside temperature is 35 degrees Celsius. The temperature inside the house is 27 degrees Celsius. Now, in our house, water from sources like cooking, bathing, sweating, cleaning, plants, and water leaks will use the surrounding heat as latent heat and evaporates. And it's mixed with the dry air inside the house. The water vapor mixed with dry air is called humidity. This humidity is measured as a percentage. Now, the house has both 27 degrees Celsius sensible heat and humidity, that's mean latent heat. Let's say the humidity is 80%. So, sensible heat is 27 degrees Celsius and humidity is 80%. Now, in the room with a sensible heat of 27 degrees Celsius and a latent heat of 80% humidity, we will feel a temperature of 30 degrees Celsius. Even if the AC remote shows the room temperature 27 degrees Celsius, we will still feel like it is 30 degrees Celsius because of the latent heat in the form of humidity. This is why weather reports often say that the outside temperature is 27 degrees Celsius, but it feels like 30 degrees Celsius due to the humidity. In the future, we will upload a video on the topic of humidity and explain how humidity makes us feel hotter. Now you have an idea about the problem of latent heat. Now let's see how to control it. Normally, all AC units reduce humidity levels. The entire process of
So, that is, something about latent heat. You should have this down. You can find this following you can find this following document, I'm just gonna show you. So latent heat plays a crucial role in many atmospheric processes, like formation of towering clouds, seen on warm summer days, and it is the major source of energy for violent thunderstorms, tropical storms and hurricanes. It's the major source for those big storms, hurricanes, thunderstorms, tropical storms, all those things. It's the major source, the latent heat, the heat that isn't measured by the movement of molecules. It's released or heat absorbed. So in this particular diagram, this is latent heat. So here we have ice. In the process of melting, heat is absorbed. So melting, you wouldn't think, well, no, how can that be? Well, heat is absorbed here by the ice, and it's resulting in melting. And then water here it absorbs heat additionally, and then it results in the process of evaporation where this water turns to gas. So ice melts because of heat absorbed. Water evaporates as a result of absorbing heat. So it becomes gas, and then back in the other direction. Condensation happens when heat is released. So out of the gas here, this is gas, it's vapor. When it condenses, when heat is released, it lets go of heat, it condenses back into water. And when this results in freezing, more heat is released, resulting in freezing to produce ice. So you have from ice to water vapor, heat is absorbed, and it's sublimation. When water vapor is heat is released from water vapor to ice, it's deposition. So this kind of, if you can, in your book, this used to be standard. This was illustrated in your book. This whole, but I didn't look. When I looked, I didn't see it anymore. But it was, it's a good visual anyway of this thing. No, we don't. But you can get, well, I'll put this up so you can look at this if you want to. You can probably, you can Google latent heat and you can probably see this illustration because it's pretty clear. It tells how much is absorbed, how much heat is absorbed, how much heat is released, but it goes from melting to evaporation, and both those processes, heat is absorbed. Ice absorbs heat, the molecules that are absorbing heat, and they absorb it until they become liquid, and then the liquid absorbs heat until it becomes a gas, and then it goes backward. So energy absorbed by water molecules during evaporation is used solely to give these molecules the motion needed to escape the surface of the liquid and become gas. During this process of evaporation is the faster moving molecules that escape the surface. When they leave, the average temperature of the water decreases, causing a cooling effect. That is what happens when we sweat. And I'll talk about that in a minute. The molecules of liquid water are always in motion. At ordinary temperatures, evaporation is slow because few molecules have enough energy to escape the liquid surface. As they absorb heat, like energy, like sun on a lake, they speed up and are better able to leave the surface and evaporate, change to water vapor. That's what happens when they evaporate. So that moisture then goes into the air, atmosphere. So you have water vapor entering the atmosphere from evaporation. Evaporation's on you, so evaporate rates increase with an increase in temperature. And then we have humidity.
That's how it feels sometimes.
Hmm?
That's how it feels sometimes.
It does. When I worked in Hawaii, my hair was really curly when I was young. And I had kind of a fro, not because I decided to grow it that, I just had it long, but it was so curly that it just. So that's what happened here. It got frizzy. So humidity is the amount of water vapor in the air. That's what humidity is. How much water vapor is in the air. But relative humidity is a percentage, just like the guy in the video said. Relative humidity is the amount of water vapor in the air is holding as a percentage of the total amount it could hold. So I'm gonna illustrate this. The amount of water vapor the air is holding, expressed like humidity is the amount of water vapor in the air. So there's this much water vapor in the air, but relative humidity is how much water vapor is in the air as a percentage of all the air can hold. And when the air is warmer, it can hold more water vapor. Just like you could have at 32 degrees, well, we're gonna see that. So relative humidity. That says the amount of water air can hold at 10 degrees centigrade, which is 50 degrees. So let's say at 50 degrees, the amount of water vapor air can hold, it's this much. That's 100%. It can't hold any more. If it gets any more water vapor in there, it'll start raining. It'll condense. You don't see this, but all of a sudden you will. It'll start condensing. But then because of 50 degrees, it can't hold anymore. But if you increase the temperature from 50 degrees to 68 degrees, so 10 degrees centigrade, 50 degrees to 68 degrees, the water vapor, same amount of water vapor, well, the yellow indicates how much water vapor air at 68 degrees can hold. It can hold a lot more. It's warmer air, it can accommodate a lot more water vapor. So this 52 degrees, this is only 52%. It's 100% at 50 degrees, it's only 52% if it's 68 degrees. And if you increase it by another 10 degrees Celsius to 86 degrees, then this amount of water vapor, this water vapor hasn't changed. The amount of water vapor in the air hasn't changed, but the air getting warmer can accommodate a whole lot more. This is only 28% of what the air can accommodate. A little more than a quarter. It could accommodate, this is a quarter, so 75% more. You could get more water vapor in this before it's saturated or 100%. Because the saturation, this air would be saturated. This 50-degree air, if it had this much water vapor, it would be saturated. Couldn't hold any more before it started to do something. So warm air can hold more water vapor than cold air. You know that. When air with a given amount of water vapor cools, its relative humidity goes up. So, like in this diagram, if you took this 30 degrees and you cooled it to 68, it'd go from 28% relative humidity to 52%. The relative humidity would go up as the temperature cools, because it can't hold as much. Relative humidity is a percentage of how much water vapor is in the air and what percentage that is of what it can hold altogether. This air right here can hold a lot more. This can't hold as much. This air is saturated, can't hold any more. When the air is given an amount of water when air with a given amount of water warms, its relative humidity goes down, it falls. Just like this. Relative humidity goes from 100% to 52 to 28. This increases 10 degrees Celsius. You get a decrease in relative humidity. So, you need to think about that so you understand it, because you'll get questions like that, and it's easy to get, one's going up, the other's going down. You need to have it clear what happens, going both directions. With this in mind, we can say that the water vapor capacity of the air is temperature dependent. So the water vapor capacity, how much water vapor can be held in the air is depending on how hot or cold it is. Warm air has a greater capacity to hold water vapor than does cold air. Relative humidity is 100%. When it's 100%, the air is said to be saturated, it had reached its dew point.
Oh, nice.
I get it.
It took me over 30 minutes to find that when I went through. So I invested a lot of time in this one part.
I would've made
Yeah,
it.
you gotta do the do, man.
Yeah.
I would've made that.
So the dew point is actually the temperature the air needs to be cooled to reach its saturation level. That one at 50 degrees, it was at saturation. You couldn't get any more water vapor until if you get more water vapor, it'll start to condense. If the dew point temperature were cooled additionally, condensation would occur. Water vapor would be changed into a liquid. So that's what condensation is. It's when water vapor that's in the air is changed to a liquid, you get condensation. You get it on your car, you get it on the grass, you get it all kinds of places, but that's where water vapor had cooled until the water, you couldn't hold any more. Just like coming out of the shower and the mirror is all foggy. You're in a room, it gets really warm, but the surface of the mirror doesn't warm up as the same as the rest of the room. So the cold surface of the mirror, the water condenses. You take an Ale-8 out of the refrigerator and you put it into the air. Well, it's right around the bottle is very cool. So you get condensation, like dripping liquid, because the bottle is so cool and the air around it is warm. So the air can hold a lot of moisture around it, but when you get right around the bottle, it can't hold as much. So it condenses what's around right around the bottle. So this is maybe a better example. So these are the temperatures over here. And this is a relative humidity. And this 100% is saturated. That means, well, at 32 degrees, you've got a little less than 5 grams per meter of water. You don't need to memorize these numbers. Just see this number is smaller than this one, or this one is larger than this one is larger than this one's larger here, larger here, larger here. So this is the largest, 30.4 grams per meter, cubic meter. Should have a 3 on these things. So that's how much water is. That's how much water. Well, at 32 degrees, with this little bit of moisture in the air, this thing is saturated. You put any more moisture into that thing, it's going to start condensing. But as the temperature increases, 32 to 43, the saturation level, it can hold more. Can hold more, can hold more, can hold more, can hold more. So at 86 degrees, you could have 30. You could have over 7 times, about 7 times much more water to saturate 86 degrees than you can at 32. So we'll visit this